Okay, lesson 36 is critical numbers. Critical values, critical numbers, a big topic in calculus and as we talk about derivatives. Okay, so I would consider it probably an application, just, of derivatives, of a way we use derivatives. So, definition. A critical number of a function is a number c in the domain of f, so in the domain of the function, where either the derivative at c equals 0 or the derivative at c does not exist. Okay, so talking critical numbers here, and when we talk about a critical number, there's two options. Either the derivative equals 0 or the derivative does not exist. Now, in this picture here, these are instances where the derivative of a function does not exist. And the first two, right here, the derivative does not exist at 0. Okay, same thing here. The derivative does not exist at 0. The derivative does not exist when there's what we call a hard or sharp point. Okay, it's different if there's a curve. The derivative exists if there's a curve. But when it is a hard or sharp point, that is in a situation where the derivative does not exist. So I'm just going to write on here, no sharp or hard points. I don't know which vocabulary word you want to use there, but that's the idea. So, like this first graph, do you guys know what this graph is?
That's the absolute value.
Yeah, this first graph would be y equals absolute value of x. So the derivative exists everywhere else because it exists on the two sides of the v, except at that hard point. Is that 2/3? Yeah. So this one is actually y equals x to the 2/3. Whoops. And it's the same thing. It has that hard point there where the derivative does not exist. And then on this last one, what happens is when we try and draw the tangent line, okay, here at 0, 0, what happens when you draw a tangent line here at 0, 0? My tangent line is going to end up vertical. And what is the slope of a vertical line? No, vertical line is undefined.
Yeah.
Okay, and so this is actually a portion of not x to the 1/2, x to the 1/3, but the idea is right here, the slope of that line, the slope of a vertical line is undefined, and the tangent line is undefined at the point 0. The rest of it's fine, but at that point 0 is the problem. Okay? Now, those are all examples of where the derivative does not exist because of the tangent line. What about when the derivative is 0? What kind of tangent line are we going to have when the derivative is 0?
Is that perfectly horizontal?
Okay, so the slope is 0 when the line is horizontal, yes? When is a tangent line horizontal then? What's going to be happening there? What characteristic is that graph going to have?
So would it be like at a max, you have a horizontal tangent?
At a max, you'll have a horizontal tangent line, and at a minimum, you'll have a horizontal tangent line. Okay, so critical points are occurring at these unique, like hard, sharp points, places where you get a vertical tangent, and where there's maxes and mins. So, key point right here. If f, so if the function has a local or relative max or min at a certain point, and that's what I'm just talking about here, max or min at a certain point, then it is a critical number. And again, that basically, not always, but basically, we're talking about there where your slope is 0. Okay? So those all together are critical points, numbers that you would investigate depending on what we're being asked to do. So So on this graph here, it says all the following places are local relative max or minimums of the function drawn. So what do you notice here? Why is this first one a critical point? It's a hard point, right? The derivative does not exist at that point, right? What about this next one? Okay, it's a minimum, and so there's a horizontal tangent line. Your slope would be 0. What about this top one up here? The next one, it's a hard point again, so my derivative does not exist. Next one is a minimum. Your tangent line is horizontal, slope is 0. What about the last one? Yep, horrible drawn line. Let's try that again. Yeah, there you go. It's a max, has a horizontal tangent line of 0. Okay, those are all places, critical numbers.
So why doesn't a derivative exist at points? Is there a reason?
It has to do with what will, like, for instance, when we take the derivative here, x will end up in the denominator. And when x is in the denominator, that point can't exist when x is 0.
Oh.
That's what it essentially ends up having to do with. Okay. So, okay, let's look at the next example. This is the example at the bottom of your page, I believe. Yeah. It asks us to find the critical numbers of this given function, and it also asks us to find where the relative maximum and minimum values occur. So, based on our topic of conversation today, what do we need to find? We're given the function. What? Well, eventually, yes, we're finding the critical value. So we're finding C. But how do we go about doing that? When do critical numbers happen? When the derivative is equal to 0 or doesn't exist. So what do we need to start off finding? We have to find the derivative. This would fall into the category of a non-calculator problem. Okay, this would fall into the category of, on the AP test, you would not be using a calculator on a problem like this. Okay, you would be doing it all by hand. Which means you can't look at the calculator and say, okay, where are my mins and maxes? Okay, just telling you up front. Not that you can't check it when you have that calculator availability, but okay, guys, derivatives, here we go. Derivative of x cubed.
3x squared.
Move that 3 out front, subtract 1 from the power, 3x squared. Derivative of 9/2 x squared, 9x. Derivative of 6x, 6. Derivative of 5, 0. Okay, so we can agree that the derivative is 3x squared plus 9x plus 6. Well, what do we do with this derivative? We want to know where the derivative either doesn't exist, which we'll worry about, that's just, I mean, what is, if we look at this x cubed plus 9, this graph right here, this is a cubic, right? We know the type of shape it is. Our derivatives are going to exist here. Our concern is where does the derivative equal 0. So our plan here is that we're going to take the derivative and set it equal to 0. So 3x squared plus 9x plus 6 equals 0. Thoughts on solving?
So we could divide by 3 and then complete the square.
I like the divide by 3. Let's not make the rest of it that difficult, though.
We do the product, so you divide by 3.
Okay, so first of all, this is an equation, right? It's an equation with both sides. If it's a function, we have to factor the 3 out. But this is an equation. We can divide every piece by 3. And so then I end up with x squared plus 3x plus 2 equals 0. And this is where I said I don't like complete the square because that's way too difficult for this level of a problem. X squared plus 3x plus 2 factors, right? X squared is x and x. What are my values I need? Two and 1, right? Multiply by 2, add to be 3, plus and plus. What do I actually do with these parentheses now? Officially, you're setting each part equal to 0. So x plus 2 equals 0, x plus 1 equals 0, and we have values of -2 and -1. You have just found your first set of critical numbers. Okay? Those are your critical numbers. Now, that's not what the question asked, though, I don't believe. It started off, find the critical numbers, okay, check, of this function. Also find where the relative maximum and minimum values occur. So, these critical values, not guaranteed, but likely represent mins and maxes. Maybe both maxes, maybe both mins, min, max, something. Now, there's a couple of different ways we can figure this out. And it all kind of depends on the situation, what we're doing. First of all, what was my original equation? It was a cubic, right? So, what could a cubic graph for x cubed plus 9x squared plus 6x plus 5 look like? We talked about this the other day, right? The basic cubic does this, right? Or a more, and this is because it's x cubed, it looks like this, and it's a positive x cubed, so it's increasing. A more fancy cubic might have the jog in it, right?
So that's the one.
Right, so because, here's the deal here, because my slope equals 0 twice, this is the version we're probably looking at. And I'll tell you, because there was an x squared next term in there, this is the version we're probably looking at. In other words, we're probably looking at a max and a min. Okay? Now, knowing what I know, I can tell you which is my max and which is my min, but it specifically wants the maximum and minimum values, which are my y values.
So we plug each of those x's in.
So we're going to have to plug them back into the original equation. Okay, now, -2 and -1. Think with me. Which one represents the max? Which one represents the min?
The max is -2.
Why is the max -2?
It comes first.
Because as we move on this graph left to right, the max occurs first, and -2 occurs before -1 on an upper line. Does that make sense what I'm saying there? Okay, so I know, without doing the math yet, my max is going to be where x equals -2. Because it wants the minimum and maximum of values, those are the y's. So, okay, when we say plug -2 in, you're going back to the original equation, not the derivative. We want the min and max values on the original equation. So I'm doing -2 to the third plus 9/2 times -2 squared plus 6 times -2 plus 5. my math served me. I ended up with negative 8 plus 18 minus 12 plus 5. Do I need to, are we okay with that? Sorry, I kind of did that on my own without thinking. Negative 2 to the third, negative 8. The one, I guess, negative 2 squared is 4. 9 halves times 4. So for me, I cross-canceled 2. And I end up with 9 times 2 is 18, minus 12 plus 5. So right there, we have f of negative 2 equals 3. And so the ordered pair is negative 2, 3. And we have already decided that this is a max. So officially, the maximum occurs at negative 2. The max value is 3. So if we want to talk about what is the max value, that is 3. And we have to do negative 1. So f of negative 1, negative 1 to the third, plus 9 halves times negative 1 squared, plus 6 times negative 1, plus 5. Negative 1 plus 9 halves, that was weird, plus 9 halves, minus 6, plus 5. This is one where I personally am going to do the whole numbers first and come back and get the fraction here in a moment. That's me, if I'm doing this mentally. Negative 1 and negative 6 is negative 7. Negative 7 plus 5 is negative 2. My brain says 9 halves is 4.5. So I'm saying negative 2 plus 4.5 is 2.5. Or I guess maybe you said negative 2 is negative 4 halves plus 9 halves, which is 5 halves. Still 2.5. However you do this. So f of negative 1, I have 2.5 written down in my notes. Doesn't matter if you say 2.5, 5 halves. So negative 1, comma 2.5, and this is my minimum. And that means my min value is 2.5. Now, we'd already talked about which was the max and min based on what we expected the graph to look like. So we knew the max came with the smaller x coordinate. How do I know which is the min and max just by looking at the ordered pairs?
Larger y value.
Yeah. Larger y value makes this the max. Smaller y value makes this the minimum. Okay? That is based on the fact we knew that there was a max and a min. Okay. Questions there? It's a lot of work by hand, but it's not, I don't think of it as exceptionally hard work here. Okay, well, here we go. Basically repeat the process, right? Try again. Find the critical numbers of the given function and indicate where the relative max-min values occur. So, I like to have my equation right here, so I'm going to copy it over. F of x, 1/4 x to the fourth, minus 1/3 x cubed, minus x squared, plus 5. What are we doing to find critical numbers? Derivative. So f prime of x. Derivative of 1/4 x to the fourth.
X to the third.
Love it when that happens, right? X to the third. Minus derivative of 1/3 x cubed. X to the second. Minus derivative of x squared. 2x plus derivative of 5. 0. What do we do now that we have that derivative?
Set it equal to 0.
Yep. Critical values, folks. Derivative equal to 0. So x cubed minus x squared minus 2x equaling 0. Thoughts?
So factor out an x.
And notice he used the word factor out an x. Do we want to divide everything by x? No, because we don't want to divide the x out of the problem. If you divide the x out of the problem, you should divide it away one of your answers. So because this is a variable, we need to factor out the x. So you factor out the x, and then in parentheses I have x squared minus x minus 2. Okay, now what? Yeah, keep that x out front, and things are being nice to us. This factors, right? X squared is x and x. I know my numbers are 1 and 2. Positive 1, negative 2. And officially, what do we do now? Set them all equal to 0. How many numbers is this? This is 3. So x equals 0, x plus 1 equals 0, x minus 2 equals 0. And what are 0, negative 1, and 2? These are your critical numbers. Okay. So we can jump right into finding mins and maxes. However, we've got 3 this time, don't we? So just finding the y values isn't going to fully tell me what's a min and what's a max. Okay, it was, when I had 1 min, 1 max, it was pretty easy. So what's my original graph? Yeah, this is an x to the 4th. So it is a quartic. Okay, we talked the other day about quartic options. What could my graph look like here?
Squared off.
Okay, a squared off parabola. And the variations of this were basically what? W's, right? You could have an even W, or you can have a lopsided W. What do we know here? Which of these options is it not?
It's not, you just know the parabola.
Yeah, it's not the one that kind of looks like a parabola, is it? Because our slope equals 0 3 times. We have 3 critical values, don't we? So it's got to be one of these others, which means what are we looking to find? We should be finding 2 mins and a max. Now, as we think about this, and here's the deal, because they are relative, we don't know, I guess I should reinforce, you can't just tell by looking at the y values what's min and max necessarily, because it could be you could have a min in one spot, and depending on where things go, you could have how do I want to say this? It's a relative max or min. And so just because, I was going to say, I'm trying to think, does that max have to be the highest value there?
it work? If
Maybe
I
it
said,
does.
like, the max would have to be in between the two other y values, because that's how I was thinking.
Well, and in terms of, and this is where we want to look at in terms of x values, right? So the values we have here were 0, -1, and 2. So if we go in order, the first one is f of -1, f of 0, and f of 2. What do we know about these once we find them?
So -1 is going to be a min, 0 is going to be the max, and 2
Right. Okay, so -1 is going to have to be a min because it comes first in the x value order. At 0 is going to have to be a max, and at f of 2 is going to have to be a minimum. With that in mind, we can plug all the math in and do all the math by hand. We can plug it in on the calculator, or I could just tell you if you want to speed this up. I have them written. Here's what I know is I have them written down, and I don't have work written down here, so I can tell you in the past I've probably just, like, we've just either put them in on the calculator or I don't know. But you guys know what to do to plug them in, right? So I have f of -1 is 55/12. I have f of 0 is 5. I should have made you do that one. That would have been the easy one, right? F of 0 is 5, and f of 2 is 7/3. So I have a minimum at -1, and that is 4 7/12, if that helps you a little bit, you know, numerically. 0.5 is a max, and 2, what is that? 2 1/3 is a min. It is 2 1/3, isn't it? Yeah. I have 2 2/3 written in my notes. I think that's a. Obviously, I didn't know what I was doing there. Geesh. Okay, questions on this?
So I think it's pretty straightforward.
It is.
It's not really.
No, I mean, this is the basics, of course. Obviously, there are tricks and everything, and, you know, there are tricky times and stuff. But this is a basics for a lot of our derivative applications. Set the derivative equal to 0, find those critical values. We talk a lot about using this to find mins and maxes. Okay? And this is, you know, you don't necessarily have the calculator at your disposal all the time. So
why did you say we don't need to worry about, like, when it doesn't exist?
well, that doesn't exist are more special cases. You know, in a traditional, like this is a traditional quartic. In a traditional quartic, you're not going to see a hard or sharp point in the middle of that. Okay? Doesn't exist are more of special cases like when you end up with a 0 in the denominator of the derivative, those type things. So really we come across those more later. More the focus today is, okay, when the derivative equals 0, how do we do that? The derivative does not exist is more right now just when you look at a graph being able to identify the hard sharp points. Does that help a little bit? Okay. Now, and this kind of goes along with special cases, but let's look at example 36b here. Not every critical number produces a local max or min. For example, x to the third. Okay, as we look at x to the third. Okay, well, let's just go through this. If f of x is x to the third, and we're looking for critical numbers, which means we need to find the derivative. What's the derivative of x to the third? 3x squared. And officially, what do we do to find critical values then? Set equal to 0. If you set 3x squared equal to 0, divide by 3, take the square root, you get 0, okay? So x equals 0 is our critical number here. Okay. X equals 0 is our critical number. Now, think about this. You know what the graph of x to the third looks like, yes? This is nothing fancy. Y equals x to the third is your basic curve there, right? That basic cubic. Where is x equals 0 happening? Okay. This is an inflection point. Okay, so critical values will often represent mins and maxes, but on occasion, you do run into these special cases. This one is a special case where this is an inflection point. It's not a min or a max. Besides the fact, if this is x cubed, you'd have to have a pair of critical values to make this work, because you'd have to have a min and a max. You couldn't just have one min or one max and it be a cubic. And so this is an inflection point. So, again, special case. And we'll learn more and deal more with these as we go through. But this is why it's important, last year, those 12 graphs that, I wanted you to be familiar with and know. This is why when we talked about the cubic options and quartic options last week, earlier this week, I guess it wouldn't have been last week. That was fall break. So earlier this week, it's good to be able to visualize the shapes. Because, half of your AP test, you don't have your calculator to rely on. So we have to use our brains here. Okay? I think that's my last example, isn't it? Yes. Okay. We have some time. Oh, whatever.
The streak did continue last week.
So you got your homework done before you left?
Yes.